All right, welcome to chapter 13 about vector valued functions. It's often useful over the rest of the study of multivariable calculus to consider functions that take some real number as an input and return a vector. And specifically, we're going to be considering these vector valued functions. We're going to be considering ones of this form, r of t. So it takes in some parameter t and returns a vector r. Equal to f of t, g of t, h of t, or if we want to write f of t I hat plus g of t j hat plus h of t k hat. And again, this is what's called a vector valued function. These three individual functions, f, g, and h, sometimes we refer to these as the component functions. And what does a vector valued function like this actually mean? Well, what it means in practice is that if we draw some nice axes here, for some particular value of t, we might have a position vector, right? That looks like this. That looks like, r of t1. And at some time later, we might have a different position vector, r of t2, and so on. And one way to visualize this is that if you imagine the tip of this vector as t changes, you could imagine that it sweeps out some kind of curve. And maybe it does some interesting things. And we call this curve a space curve. So often we will investigate what are these space curves, what do they look like, and how can we describe them. Now, we can actually write these in a slightly different way that is maybe more in line with what we've already seen. We could take a look at these component functions and say, well, this is just the same as a parametric curve, where x is equal to f of t, y is equal to g of t, and z is equal to h of t. These are, of course, our parametric form of our equation versus our good old vector form here. And this vector versus parametric form might remind you, we've actually seen these before, these vector valued functions before. We've seen lines. It just happened that all of our component functions were linear for a line. Now they're allowed to be whatever. So let's try to sketch one space curve. It's actually one we'll be working with an awful lot this year. And so I'm going to give it to you right now. This is r of t equals cosine t I hat plus sine t j hat plus t k hat. And our objective is going to be to try to sketch this and see what it looks like. So if you look at the first two terms here, the cosine t I hat plus sine t j hat, this might be somewhat familiar to you or suspicious. You see like x looks like cosine, y looks like sine. This is, of course, a unit circle. So it kind of traces out a unit circle in x and y, but also as t goes by, it's also going up. Our z-coordinate is getting bigger and bigger and bigger. And so we can start to get an idea here by plotting a couple different points. If I plug in t equals 0, I'll get a nice point here. I'll get, like 1, 0, 0. If I plug in pi over 2, I'm going to get 0, 1, pi over 2. So it kind of slews around this way and curves up. And if I actually plot the whole thing out, and I'm going to butcher it drawing it a little bit because I'm going to get kind of this spiral that starts out, and you might imagine having a point here, 1, 0, 2 pi. When it comes all the way back around, it's going to spiral upwards. From above, it'll look like a circle. From the side, it'll actually look like a sine or a cosine function. And this is a function we'll be seeing a whole lot. This is a space curve called a helix. So we will be messing around with a lot of helices this year. we turn our attention now to what we can actually do usefully with these vector valued functions. And this being a calculus class, you might expect that we want to possibly take some integrals, take some derivatives, or some integrals, and these are both things you can do. Let's start with the derivative. The derivative has its normal definitions, the rate of change and everything like that, but it has a limit version of the definition, which we will not really ever use. R prime of t is the limit as h approaches 0 of r of t plus h minus r of t all over h. And you might imagine, again, if this is, r of t, and this is r of t plus h, that delta r, that between them, kind of runs along our curve. And so what we actually find is that we can define actually r prime of t in a more useful way, which is we actually just take the derivatives of each component. For this, it's just the derivatives of each component function. It's really quite simple. So for instance, if we wanted to start with our helix cosine t sine t comma t, that r prime would in fact be negative sine t cosine t comma 1. There are a couple really important points here about these derivatives. So some key points here. First key point is that you can interpret r prime as being a velocity vector. It is kind of like our velocity vector in physics. And in fact, r prime is always tangent to the curve. So if I were to actually find r prime here, it's our velocity vector. It tells us which way we are moving at any given moment along a curve, and is always tangent to the curve. We can actually therefore define a unit tangent vector as being r prime divided by the magnitude of r prime, and we'll have some use for the unit tangent vector soon enough. You can integrate. We don't do quite as often, and when you do integrate, in fact, what you'll find is you just integrate each component. So the integral of r is just the integral of f times I hat plus the integral of g, j hat, and so on. We will do some examples of that in class. And you can take further derivatives, right? So you could do r double prime, which would just be like v prime, which is, like in physics, an acceleration vector. And we'll do more with acceleration in 13.4. So I want to do just a quick work example. This actually does come up on your problem set, and so I thought it was worth doing because it's a little strange. And the question that it asks you is it wants you to show, it wants you to show that if the magnitude of r is constant, then r prime is always perpendicular to r. So I want to break this down and first of all ask, what does this even mean to have the magnitude of r be constant? One way to interpret that is that in 3 dimensions, you're always on a sphere. And what I mean by that is, think about what a sphere is. A sphere is a set of points equidistant from the origin. So that means that if your position vector always has a magnitude of c, you are constrained to live somewhere on this sphere. In order to actually prove this, we're going to do a little bit of a funny thing. You might suspect, hey, we're trying to find something that's perpendicular. Maybe we want to have a dot product. And we're actually going to start with kind of a weird dot product. We're going to do r dot r. We happen to remember, maybe from the beginning of chapter 12 that r dot r is in fact the magnitude of r squared. So r dot r is c squared. So what we're going to do now is we're going to take a derivative of the dot product r dot r. Now you can take the derivative of dot products, and it in fact follows the product rule. So what you'll do is you'll go, r prime dot r plus r dot r prime. Now in this case, dot products are commutative, so r prime dot r and r dot r prime are the same. So we can just write this as 2 r dot r prime. Now, you might ask, if we took a derivative of this, what happens to the other side? Well, what is the derivative of c squared? C is a constant. So the derivative of c squared is 0. Therefore, we have just shown, dividing by 2, that r dot r prime is equal to 0. And you might say, Mr. Bates, well, so what? We did some math. What does that even mean? The way to interpret this is to say, if you're stuck on the surface of a sphere, the only way you can move is along the sphere. And kind of by definition, if you're moving along the edge of a sphere or a circle, you are always perpendicular to the radius. And that's what we should. So, excellent.